Hi, in gene expression analysis, comparing two groups feels always comfortable. You cannot miss anything, you know exactly what you're doing. But what if it is, for instance, 3 groups, or even 4 groups? It might be scary if you never tried such analysis before, you don't know where to begin, but actually it is quite some fun. Suitable examples can be found in NCBI Geo. Call this number, for instance. Then you come to a data set, which is a mouse expression microarrays by Chambers and co-authors. I know this from my work when I was not yet retired. And what is interesting in this data set, cells are taken from mice of different ages, 2 samples per age, 2 months, 6, 12, 21. The rest is not so much important for us, not for the paper, of course. But this is example of 4 age groups in one factor, obviously. Then, as usual, we transfer everything into R script. So you begin, as usual, fetching data from NCBI Geo site and prepare the table, select the proper column, and then return all the sample information for age back to the G set, like this and like that. So age and months is back to the G set, and months is categorical, and age, if you ask, is numeric, at least can be converted to the numeric easily. Then we do the usual check of the data and see that it is log transformed and pretty well normalized, so we can move directly to the design. And it is one factor, it's only a month, nothing else. And then do the fit. And what we fit is so far everything. And now there is a question. For contrast, what shall we use? Of course, you can use 2 out of 4 groups, like this, for instance, comparing 6 months to 2 months. But then you realize that 2 and 6 is formally speaking, young mouse. Then the fun begins. You can say, I can compare 2 months old plus 6 months old versus 12 and 21. Technically, when you say plus, it means you will add values literally to every gene expression from date of 2 months to date of 6 months, and therefore if there are 2 data sets, you divide it by 2, take an average. In case when you have it equal, compare 2 against 2, you can skip it. But in case if you compare, for instance, first 3 data points, 2, 6, and 12 months together versus 21, and forget to divide by 3, then this group together will be overwhelmingly upregulated because it's a 3 times expressions data, so then it will be a huge bias. Don't do it. I hope you got the idea. When there are more groups, you can do this simple math and combine groups together, or you can also ask, what if I compare adjacent time points with one another? 6 minus 2, 12 minus 6, and 24 minus 12. Let's you take this one. And the last option, I thought, also makes sense if you compare all other age groups to the 2 months and then check. What will happen then, it's also entertaining. You do fit 2 and bias and decide tests and then summary. And then summary appears, which is not trivial. Instead of 1 column of summaries, you have a 3 column of summaries. You can do it a bit more stringent with LFC1, meaning log fold change 1, 2 times difference, or without it, it doesn't matter. In both cases, number of differentially expressed genes are small, because time interval is small. But we are mostly interested in principles of such analysis. And if you compare everything to a month 2, and then repeat the stuff, and also you demand that log fold change is 1, then ask for it, then you see that there is a gradual increase in the number of differentially expressed, so more time you wait, more differentially expressed genes you get. So that's the fun stuff, and the rest is not so much important. Another illustration to this simple math business can be drawn out of this example by Laurenti, first authors, and others from 2014. This time it is human hematopoietic cells of many different lineages. It's better to move to the paper itself, where it is nicely illustrated over here. Authors used cord blood, and then hematopoietic stem cells were isolated out of those cord bloods, and all other cell types shown here on left and right pictures. Altogether they form a differentiation tree. For instance, HSCs differentiate in MPPs, then it splits on lymphoid lineage to T cell progenitor B cell, and common myeloid progenitors to granulocytic, etc., and erythrocytic lineage. So when you look at it, and when you look at the data, then you puzzled immediately what I supposed to compare here. Of course, you can limit your scope to compare HSC1 with HSC2, for instance, or MPP, but then you don't use the full power of the data set. Instead, you can go again into the business of multiple contrasts. Again, these are microarray data, and therefore we use limma and geoquery to fetch it from NCBI geosite. Then we extract sample information. Then we have to work on this cell type because it has extra underscore symbol, and we will split those names by underscore and make a sample table. First replace, then extract the information, and then we have this long line of cell types and replications, which are actually cord bloods. So which cord blood was used for what cell type, which is rudimentary to our exercise. And then of course we check how about data, and they are all log transform and normalize. So we return cell information back to the gset, and then run just a simple one-factor design. And column names of design are those. So there are many different cell types. We do the first fit, and then we do the second fit, and with the second fit, on the basis of the given tree of differentiation, you can decide whether you take a erythroid lineage, then you will be interested in this sequence of differentiation, or you choose a T cell lineage, then you have to think about this one. Whatever branch of the differentiation tree you prefer, you decide the trajectory, and then you play with the multiple contrasts, literally building up the change in the cell type. So HSC2 minus 1, MPP minus 2, MLP minus MPP, ETP minus NLP. That's exactly the sequence of events from HSC1 to ATP. Again, contrast matrix accept this fun. Then we do a contrast fit, then eBias and top table. We reduce a bit, and then call for decide tests and the summary. And then again, even without any further pictures, etc., you see quite a useful information that it appears that the scale of the differentiation between all those types is not linear at all. So the distance in differential gene expressions between HEC1 and 2 is 3 genes down and 4 up. MPP to HEC2 step 1 is already 813. The next step is 700 to 262, and the last step is already counting in thousands. In fact, what we were able to do is to scale those distances between those nodes on this dendrogram in natural way. Actually, these numbers, what authors show you, is about the same story. They measured a number of up and down regulated genes, and you can find details in their paper, of course. And you can think it's a lot of work. Yes, it is if you don't know the tricks, but if you know them, it's quite some fun.